Good morning. Believe that you are beautiful and have what it takes to move mountains, and you will move mountains. Do not allow yourself to be let down by what others say. Get up and do what you can do best. Good morning to one and all present here on behalf of PG and Research Department of Mathematics, DG Vaishnav College, Chennai. I welcome all the PG students and CSIR aspirants. God can handle your doubt, anger, fear, grief, confusion, and questions. You can bring everything to Him in prayer. Now, Tamutai Vatu followed by college prayer.
நீராறும் கடலொடுத்த நிலமடந்து எழிலொழுகும் சீராரும் வதனமென திகழ்வரத கண்டமிழே எக்கணமும் அதிசிறந்த திராவிடனல் திருநாடும் தக்க சிறு பிறை முதலும் கரித்தனரும் திலகமுமே அத்திலக வாசனை போல் அனைத்துலகும் இன்பமுற எத்திசையும் புகழ் மணக்க இருந்த பெரும் தமிழனங்கே தமிழனங்கே உன் சீரிழமை திறம் மிகுந்து செயல் மறந்து வாழ்த்துதுமே வாழ்த்துதுமே வாழ்த்துதுமே.
सत्यव्रतं सत्यपरं त्रिसत्यं सत्यस्य योनिं निहितं च सत्ये सत्यस्य सत्यं ऋतसत्यनेत्रं सत्यात्मकं त्वां शरणं प्रपन्नाः वाणी गुणानुकथने श्रवणो कथायां हस्तौ च कर्मसु मनस्तव पादयोर्नः स्मृत्यां शिरस्तव निवास जगत्प्रणामे दृष्टिस्ततां दर्शनेस्तु भवत्तनूनाम् नमो भगवते तस्मै कृष्णायाद्भुतकर्मणे रूपनामविभेदेन जगत्क्रीडति यो यतः ॐ शान्ति शान्ति शान्तिः.
This is C4 workshop, Chase, Crack, Conquer, CSIR Net, which will make CSIR aspirants to go to the next level. Today, our resource person, Dr. R. Sivaraman, Associate Professor, PG and Research Department of Mathematics, DG Vaishnav College, Chennai. Now, I hand over the session to you, sir.
So is the screen visible? Hello?
Yes, sir.
Hello?
Yes, sir. Yes, sir.
Please answer me. So shall I begin now?
Yes, sir.
Hello?
Yes, sir.
So good morning to one and all. We begin our today's C4 class. This is 17th session of this class conducted by our department. And today being 7th February 2021, this is actually 144th birth anniversary of important mathematician G.H. Hardy, who's shown in the picture. And he was responsible for bringing Ramanujan's genius to the world and helping him all through the way throughout his research work and assisting him in writing papers. And what else you require about Ramanujan, you have to talk about Hardy. In other words, without Hardy, Ramanujan's work and other things could not have been known as of today. So Indians owe a lot to Hardy. So that is why I have chosen to put his picture as a tribute to him on his birthday. Now let me just recall some of the basic formulas, and I will just give the ideas first and then do the corresponding problems related to the idea that we are going to present, so that people may get benefited out of this. So those who want to note it down, you can note it. So if f is a function from two sets A to B, where A is domain, B is codomain, the number of functions that can be defined from A to B is number of elements in B to the power of number of elements in A. That is number of elements in the codomain to the number of elements in the domain. This many functions can be constructed between two non-empty sets A and B, provided if A and B are finite sets. Okay. Now let us assume that for all these counting problems and formulas, we assume that A and B are non-empty and finite. Okay? If f is from A to B is onto functions are also called surjective function. F is an onto function where A has m elements and B has n elements. The domain has m elements, codomain has n elements. Then the function is onto, then the number of elements in the domain, namely m, will be greater than or equal to the number of elements in the codomain. This is because if m is less than n, then what will happen is all the elements, suppose if A has 2 elements and B has 3 elements, 2 elements in A will be mapped out to some 2 elements in B. So there will be left with one more element in codomain B, which doesn't have any pre-image, so that doesn't count in the range of the function. So it will only be into but not onto. Therefore, if a function has to be an onto function between two non-empty finite sets, then it should be the fact that number of elements in the domain should be greater than or equal to number of elements in the codomain. Similarly, if a function f from A to B is a 1-1 function, namely injective function, see, these are all equivalent terms for 1-1 and onto. Injective functions are also called onto functions, and surjective for onto. Then if the function is 1-1, then the number of elements in the domain should be less than or equal to number of elements in the codomain. Again, you can give a similar reasoning here. Suppose if the elements in domain is more than the elements in the codomain. Suppose if A has 4 elements and B has 3 elements, because if f is a function, all the elements should have a unique image in the domain. So the first 3 elements in the domain will be mapped out to 3 elements in the codomain, and therefore the 4th element in the domain should need to be mapped out to one of the 3 elements in the codomain, which is already mapped down to the rest of the 3. Therefore the function, so any 2 elements in the domain will be mapped on to the codomain element, particularly if m is greater than n. Therefore, if a function need to be 1-1, then the number of elements in the domain should be less than or equal to number of elements in the codomain. You can check whatever I said now through paper. You can just write it down and verify. So if a function is a bijective function, if it is both 1-1 and onto, then it should satisfy both these inequalities simultaneously. So m greater than or equal to n, m less than or equal to n, both of this together will give you m is equal to n. In such cases, we say the sets A and B are equinumerous. Okay, so A and B are equivalent, whatever it is. A and B are equivalent if there exists a bijection between two sets A and B, or A and B are also called equinumerous whatever it is. So they should have the same cardinality. See, that doesn't mean that A is equal to B. Supposing if A has 4 elements, B should also have 4 elements. If A has 5 elements, B should also have 5 elements to define a bijection between them. Again, this is not true for infinite sets. This is only true for whatever I'm giving here, or true only for, or makes sense only for finite sets. I mean, this property particularly will not hold true for when you take A and B to be infinite sets. Okay. Now listen. If you take A having a function such the domain has m elements, codomain has n elements, then the number of 1 functions, injective I functions between A and B is given by n permutation m, which is n factorial by n minus m factorial by definition of permutation. NPR is n factorial by n minus r factorial. So by definition of permutation of r objects taken out of n, you get this. This is quite easy to see. And if you take two equal sets, if f is a function between A to A, if you take domain and codomain to be equal sets, and if you assume that f is a bijection, and if you assume that A has n element, then number of functions that you can define, bijectives that can be defined between a set to itself is n factorial. So these are some of the things, and this formula is a special case of this formula, because if you take m is equal to n here, you get n factorial by n minus n factorial, because m is equal to n, and you get 0 factorial in the denominator. 0 factorial is 1, so you get the answer as n factorial. So, and this explains why, this formula explains why there are n factorial elements in the symmetric group of order n. See, if you talk about Sn, symmetric group of order n in algebra, it is basically each element in Sn is basically a bijection between a set containing n elements to itself, and therefore that is why you see that order of Sn is n factorial. So that is how this formula has come. This is because of this reason, you in algebra you get the fact that Sn contains n factorial elements, symmetric group with n elements. Now let f from A to B, where A contains m elements, B contains n elements, number of onto functions. Here we saw about number of into functions. Now the number of onto functions are surjectives that can exist between two sets A and B is given by this formula. This needs some explanation, but this is a multinomial quotient. So you take multinomial quotient and sum it up over all choices for R1, R2 up to Rn being summing up to n. So this suffixes should sum up to n. N is number of elements in the codomain. Okay. So let me give some examples to justify. There are one or two questions that were asked in the previous papers regarding this. At least few questions will be asked here and there, either in section A or section B, regarding this formula. So these formulas are quite important and worth noting down. Okay. So if you, all these formulas that I have shown here are derived in detail in this paper, which I published, enumeration of relations and functions, in this journal. I just took this statements from that. The detailed derivation of all these formulas were given there, and some more, of course, not only just this formula, some more have been proved in that paper. So consider the two sets A123, B123. This is asked in one of the paper, previous year paper, in part C question. Consider the two sets capital A, which is having 3 elements, and B having 5 elements. Choose the correct statement. This is being part C, more than one option might be correct. Okay. The total number of functions that can be defined from A to B is 125. Here it is 243. In among the total number of 1 functions from A to B is 60. Total number of 1 functions. See here, there's no description about onto. It is given only a total number of functions and 1 functions, because the number of elements in the domain is 3, number of elements in the codomain is 5, and 3 is less than or equal to 5. And you saw here, if the number of elements in the domain is less than or equal to number of elements in the codomain, you can only define onto 1 functions. You can define only injectives but not surjectives. You can define surjection only if m is greater than or equal to m. But in our case, m is 3, n is 5, so 3 is less than or equal to 5. Therefore, you only have possibility of defining 1 functions, but there exists no onto function between these two sets, and that is why there is no description of onto function, because there is no onto function that can exist between A and B. So no choice is given with respect to onto functions. That is one thing that you can understand before even beginning to solve the problem. So number of elements in A is 3, which is M for us. M is 3, N is 5. So number of functions according to the formulas, number of elements in the codomain to the number of elements in the domain, which is 5 power 3, that is 125. So the first option is correct. Number of functions that can exist between A to B, total number of functions is 5 power 3, that is 125. Number of one function that can exist is NPM. I told you this formula here. Number of one function that can exist between two sets A and B, where A has m elements, B has n elements, is NPM, n factorial by n minus m factorial. So here n is 5, m is 3, so you get 5 factorial by 5 minus 3 factorial. This is 2 factorial, which is 2. 5 factorial is 120. 120 divided by 2 is 60. So the total number of onto function that can exist between A and B is 60. Therefore, options 1 and 3 are correct. Okay, these two options, 1 and 3, are correct options for this problem. Now let us take I give an example. This is constructed by my own way to make you follow this formula. I don't know whether this is asked anywhere, but better knowing it, because it might be asked in future also. Let f from A to B, where A contains m elements, B contains n elements, then the number of onto functions, surjectives, that can exist between A and B is given by this multinomial coefficient, summation of multinomial coefficient, where numerator contains m factorial, denominator contains product of factorials which sum up to n, of numbers which summing up to n. Let me give an example. See, for getting onto functions, the number of elements in the domain should be greater than or equal to number of elements in the codomain. You remember, m should be greater than or equal to n for getting onto functions. So that is why I have chosen an example with m value 5 and n value 3. This is greater than or equal to this. So m is 5, n is 3. So number of onto functions according to this formula, m is 5 here. So summation over 5 of 3 indices, because there is only 3 values here. B contains only 3 values. Okay, so there are the number of indices that comes over here is number of elements in B. Because n is 3, you get R1, R2, R3. You have to choose R1, R2, R3 such that R1 plus R2 plus R3 is n. N is 5 here. Okay, so this is how the formula turns out to be. I think I made some mistake in the writing of this formula. Anyway, this indices should sum up to this number, the numerator number, the number which is written in the top. So the number of indices here is number of elements in the codomain, namely R1, R2, R3, and they should add up to this particular number, which is 5. So if you find such combinations here, of course, R1, R2, R3 are positive integers. Therefore, you can choose either 1, 2, 2, they add up to 5, or you can permute them 2, 1, 2, or 2, 2, 1. So the 1 can come in the first place, or the second place, or the third place. So these are the 3 possibilities with getting 1 adding up to 5. And you can get 2 ones, 1, 1, 3, 1, 3, 1, 3, 1, 1, and not anything more. Because if you take 4 as one of the choice, you get 1, you are not permitted to take 0. Okay, so you have to use only positive integer values here, because 0 is not allowed. These are the only possible cases upon adding up to 5. For this case, R1, R2 plus R3, R1 plus R2 plus R3 is 5 in each of this case, and no other cases. So you get 6 terms here. So these 3 terms are equal because you are multiplying the denominator with this factorial. So for example, if I want to find a multinomial quotient of 5, 1, 2, 2. This is 5 factorial by 1 factorial to 2 factorial to 2 factorial. This will be 5 factorial is 120. This is 2 times 2, 4. So 120 by 4 is 30. But you see, when you try to calculate this will also be 30, because there are 2 2's here and 1 1 here, and you multiply them in different order. Multiplication is commutative and associative, so it doesn't matter in what way you multiply, as long as you have same numbers, 2 2's and 1 1, you get all these answers to be 30. So that is why, if I know that this is 30, there's no need to compute them separately. If this is 30, this is also 30, this is also 30, so you get 3 times 30. Similarly, if this numbers here are permutation of this, in other words, there are only 2 1's and 1 3 written in different order, which means if I calculate this term, because the product of terms is commutative and associative. If I know this value, that will be equal to this, and that will also be equal to this. So you can just rewrite them. The denominator, it's only a product. So if I can compute 5113, which is 5 factorial, by 1 factorial into 1 factorial to 3 factorial. 5 factorial is 120, 3 factorial is 6. So 120 by 6 is 20. So these three values are 30 and these three values are 20 each. So you get 3 times 30 plus 2 times 20. Sorry, 3 times 20. This is each of this value is 20, each of this value is 30. So you get 3 times 30 plus 3 times 20. You get 150. So which means that there are 150 functions that can exist, onto functions that can exist between A and B. See, the total number of functions that would exist between A and B according to our formula should be 3 power 5. And 3 power 5 is 243. So among 243 possible functions, 150 will be onto function. Okay, that is what we can conclude from this calculation. I don't think this formula is not well known to other sources, so you can note it down. So my next example is concerned about a function which is 1 1 onto 1 1 into, and all those things are very basic things too. So I have not introduced much basics about here, but it's an interesting example. You consider a function f from q to r. Q is a set of rationals, r is a set of real numbers, such that f of 0 is defined to be 0, and f of any rational number put in the form p by q, where p is an integer, q is a natural number. Q is not an integer, but q is a natural number, and GCD of p and q is 1. So leave away about those conditions. You want to know whether this function is 1 1 or onto. If it is both 1 1 and onto, or if it is 1 1 but not onto. Okay, either one of them, that is onto but not 1 1, 1 1 but not onto, neither of them. So you can get the solution like this. You can to see whether if it is 1 1, I take f of 1 first. Okay, 1 is, if you write r is 1 here, I should write that in the form p by q, where p is an integer, q is a natural number. So 1 I can write as 1 by 1. And if I apply this function here, the numerator, if you take p by q, the numerator should be p, denominator should be 10 power the denominator, 10 power q. So if it is p by q, the answer is the image of the function of this value, p by q. This p comes as it is. In the answer, the image, you get 10 power this denominator. So if it is 1 by 1, you get 1 as it is, 10 power 1. 10 power 1 is 10, so you get 1 by 10. So the image of 1 under this mapping is 1 by 10. That is, if we take image of 5, which is 5 can be written as 10 by 2. This is 10, I can write the numerator as it is. The denominator, you get 10 power q. So this is q for me. This is p, this is q. So if you look at the definition, f of p by q is p by 10 power q. So this p is written as it is. This q is 2, so you get 10 square. So this is 10 by 100. That will be 1 by 10. So you see, I have taken two different numbers. So image of 1 as well as 5 turns out to be same answer, 1 by 10. That means 1 is mapping onto 1 by 10. 5 is also mapping onto 1 by 10. In the domain, 1 and 5 are different elements, clearly. Image of 1 is 1 by 10. Image of 5 is also 1 by 10. So it can't be 1 because two different elements in the domain are getting mapped on to the same number in the codomain. In other words, if a single element in the codomain will have more than one pre-image, then the function will not be 1 1. Therefore, two different elements, because two different elements 1 and 5 have same image value, which is 1 by 10 in the codomain, this function is not onto. If you guess this through known terms, like to check 1 1, usually what you do is assume f of x is equal to f of y and prove that x is equal to y. Here f of 1 is equal to f of y because both are same, but 1 is not equal to 5. Therefore, it is not 1 1. Okay. Now, to see whether it is, because the codomain is a real number. Okay. See, real numbers are numbers comprising of both rationals as well as irrationals. R is union of rationals and irrationals, isn't it? So, in the codomain, I have both rational numbers as well as irrational numbers. Now, what happens is, according to the definition of the function, if I choose p and q, where p is integer and q is natural number, then this will be a rational number. P by Q is a rational number. So if you take the image here, this is an integer, so this is integer. Q is a natural number, so 10 power Q is also natural number if Q is natural number. So this is some integer by some integer. So any natural number is an integer. So this is some integer by some integer. So this ratio is always a rational number, because you know that rational numbers are ratios of two integers. If we divide one integer upon the other integer, but the denominator is non-zero, then that is a rational number. So as whenever you choose P to be an integer, Q to be rational, Q to be natural number, then according to the function that is defined here in the question, you get this answer. This is always a rational number, because this is an integer, this is also an integer. Any natural number is an integer. So this is a rational number. And therefore, if I take any irrational number like square root of 2 or pi in the codomain, such numbers will not have any pre-image. So those numbers will never come under image of f, rather range of f. If you take range of f, you get only rational numbers. The irrational numbers won't be counted, and therefore like numbers like root 2, root 3, pi will not have any pre-image. Even if one of the element in the codomain does not have pre-image, then it is not onto function. So because of this fact, it is not 1 1, the first equation. Because of this fact, it is not onto. Therefore, f is neither 1 1 nor onto. This is part B question, so only one option is correct. So the correct answer is the last option. F is neither 1 to 1 nor onto. Now let me discuss this problem. I have discussed this formula in one of my previous classes before. Those who have missed it can go through. I think it's first class or second class I discussed about this. This is very important idea. See, you know that a set is countable if it is written as 1 correspondence with set of natural numbers capital N. If you assume that the cardinality of n is n naught, see, it is meaningless actually to assign cardinality for possibly for infinite sets like natural numbers or integers. But with respect to discussing questions like countability and uncountability, it makes some sense to do this. Only then we can analyze. Okay, for the convenience we are doing this. So if you take the cardinality of natural numbers to be n naught, usually people may write alf naught. That alf symbol, unfortunately, I could not get in the keyboard, so pardon me. And if you assume that the cardinality of the real numbers is C for continuum. So this whole idea actually comes in a big theory called continuum hypothesis. So modulus of R is C. It was Cantor who proved that both are infinite numbers. Natural numbers are infinitely many. Real numbers are also infinitely many. So this contains infinitely many elements. This also contains infinitely many elements. But Cantor showed that the infiniteness of real numbers is more than infiniteness of natural numbers. So in other words, he could, in a clever way, he could compare the infinite sizes also. It's easy to compare finite sizes. Like if you give me a number 6 and a number 10, then I can easily say that whether 6 is less than 10. In general, if you give me any two real numbers A and B, it's easily possible for me to, this is called law of trichotomy, because I have three options. Either A should be less than B, or A will be equal to B, or A will be greater than B. One among the three should definitely happen for any two real numbers A and B. I can possibly compare and decide one among these three will be there. So comparison with respect to finite numbers is always possible because of the basic axioms that we assume. But unfortunately, before Cantor's time, no one had a very apt idea or very clear, and though they have discussed about this infiniteness, the strong mathematical foundation was laid by Cantor. He actually proved that the set of real numbers are uncountable. Once you say that set of real numbers are uncountable and set of natural numbers are countable, then this cardinality C will be greater than, because uncountableness is something more than countableness. So all countable sets will have cardinality equal to n naught, not just n. If a set is countable, its cardinality will be equal to n naught or alf naught, whatever it is. See, any countable set will have its cardinality equal to modulus of n. And any uncountable set will be having cardinality equal to mod r, cardinality of the real numbers. Okay, so this infinite collection, this infiniteness is more than this infiniteness. This is what Cantor proved. In fact, those third year students who study Taylor analysis will show that set of all rational numbers are countable, but set of all real numbers are uncountable. That means that is actually what is said here. This, okay, this is countableness, this is uncountableness. Okay. Now, if you take subsets of all natural numbers, that will be of the cardinality 2 power n naught. If you take any countable set and collect all its subset, that will be having cardinality 2 power n naught. In that collection will be uncountable, because you see 2 power n naught is equal to C. So though the set may be countable, if you take all subsets, create a new set by collecting all subsets of a countable set, that will be having cardinality 2 power n naught. The resulting collection will be uncountable. If you take cross product of two uncountable sets, you get uncountable set. And therefore that is why, because R2 is uncountable, because R cross R is uncountable. So if you take R2, you can write it as Cartesian product of R and R cross R is R power 2, that is R2. That is also uncountable. Whereas if you take n naught cross n naught, you get n naught. That is, if two sets are countable, then the Cartesian product is also countable. So I have missed that writing here anyway. And if you take n naught power n naught, set of all subsets of countable set, see here I am taking set of subsets with just two elements. Here I am taking set of all subsets. Here I am taking set of all subsets with just two elements subsets here in 2 power n naught. This 2 power n naught is collection of subsets of a countable set, where each subset will have exactly two elements. Whereas if I collect set of all subsets of a countable set, you get a number equal to n naught power n naught, that is also uncountable. So these two terms, formulas, gives you a condition that if you know that set of natural numbers are countable, the set of all two element subsets of natural numbers will be uncountable, as well as set of all subsets of natural numbers will also be uncountable. You can see proof of all these results in books, but the proof will be very detailed actually, so it's not possible to mention here. But in any deeper analysis book, you can go through this proof. Probably in books like Rodin and other basic set theory books and other things, you can see about this. Even Cantor himself has written a beautiful book about this. Okay. So if you take C power n naught, that is, if you take uncountable set to the power of a countable collection, you get another uncountable set. Okay, like R2 or R3 or something like that, you get uncountable. So if you take uncountable sets R infinity, if you take R infinity, R power capital N, where N is a natural set of natural numbers, that collection, if you multiply R any number of times, as many times as possible, or take Cartesian product any number of times, you get still an uncountable set. Okay. This formulas conveys a big meaning and answers so many questions about countability as well as uncountability. So what you have to remember finally is, if you have a set whose cardinality is n naught, which is equal to set of natural numbers, then such a set will be countable. If you have a set whose cardinality is equal to C, it will be uncountable. So this is one of the easiest way to guess whether a set is countable or uncountable. So we will see this problem, which is asked in part C question, the previous year paper, one of the previous year papers. Let S be an infinite set. Which of the following statements are true? Please pardon me, I'm not well today. I mean, I have severe cold, so I could not speak continuously. So please pardon me. Let S be an infinite set. Which of the following sets are true? If there is an injection from S to N, then S is countable. If there is a surjection from S to N, then S is countable, and all those things. So 4 options are given. All things about injection and surjection. That means 1, 1 and on 2. Okay, let us check one by one. It's a very interesting question actually, which needs a bit of explanation before concluding anything. I recall the two results that I have written before, shown you the first slide. If f is from A to B is onto function, that is surjective function, where A contains m elements and B contains n elements, then the number of elements in the domain should be greater than or equal to number of elements in the codomain. Similarly, if you know that a function between two sets is 1, 1 injective function, then m is less than or equal to n. We make use of this condition here. Okay. So first case, n is set of natural numbers here. So first I take a function. So let S be an infinite set. See, any finite set is countable, so there's nothing to do there. So that is why the question itself is very clearly mentioned as let S be an infinite set. if you take any infinite set, if it is countable, then its cardinality will be equal to n naught. If it is uncountable, its cardinality will be equal to c. I do not know whether S is countable or not. Okay, any infinite set will have cardinality equal to countable set or uncountable set. In particular, if S is countable, then mod S will be equal to n naught, and if S is uncountable, then mod S will be equal to c. So the cardinality of S lies between these two terms. If it is countable, it's equal to n naught. If it's uncountable, it is equivalent to c. So it's somewhere between that cardinality of S will satisfy this inequality. Now, in the first case, if there is an injection from S to n, if F is an injection, then you see if there is a 1 function, injective function, then the number of elements in the domain is less than the number of elements in the codomain. Here S is domain, n is codomain, the first option. We'll take options one by one and discuss, okay, which is correct. If taking the first option, if you take a function f from S to n, S is domain, n is codomain, so you get number of elements in S is less than or equal to number of elements in n. Number of elements in S, number of elements in n is n naught. So what does this mean? Number of elements in S is equal to n naught, because here mod S is less than or equal to n naught. Here mod S is greater than or equal to n naught. This is always true. This condition is always true because of the problem. Okay, so I get mod S less than or equal to n naught, number of elements in S less than or equal to n naught, because assuming there is an injection. If there is an injection between S to n, then I get this inequality. Mod S is less than or equal to n naught, but this is always true. Mod S is greater than or equal to n naught. So combining these two, I get mod S is equal to n naught. So I have a set S now, infinite set, whose cardinality is n naught. And I just told you that if you have any set whose cardinality becomes n naught, then such a set will be countable. So S is countable. According to this is what I told you a few minutes back. Supposing if you take F to be a surjection between S and n, surjection onto function, then using this inequality for onto function, number of elements in domain should be greater than or equal to number of elements in codomain. So mod S greater than or equal to mod n. Mod n is n naught. So you get the same inequality here. You know that mod S is greater than or equal to n naught. Here also you are getting mod S is greater than or equal to n naught. You get same inequality. So I do not know whether know certainly about S. If S is countable, mod S will be equal to n naught. If S is uncountable, then mod S will be greater than n naught. But I do not have any information about S in this condition, because here you get mod S greater than or equal to n naught. The same condition is what you get when you assume the F is a surjection between S to n. So I can't decide conclusively, and therefore leave it as it is. It may or may not be. S may be countable or may not be countable. Depends upon. So you can't conclude to any answer. If you take the third option, there is an injection from n to S. Again, for injection, which is 1 function, m is less than or equal to n. So you get because now the function is from n to s, not s to n. The first option is from s to n. The third option is from n to s. So number of elements in the domain, namely mod n, will be, which is n naught, is less than or equal to number of elements in the codomain, which is s. Again, you get mod is less than or equal, greater than or equal to n naught. Here also mod is greater than or equal to n naught. Like the previous case, you can't conclude anything here, because this inequality is same as this inequality, which means S may or may not be countable. S might be countable or S might not be countable. So I can't guess anything from here. Whereas if we take the fourth option, if there is a surjection from n to S, the same principle. For surjection, number of elements in the domain is greater than or equal to number of elements in the codomain. Therefore, n naught is greater than or equal to mod S. But here you see n naught is less than or equal to mod S. Here n naught is greater than or equal to mod S. Here n naught is less than or equal to mod S. Therefore, mod S is equal to n naught. I have a set S whose cardinality is equal to n naught. Therefore, I can conclude certainly that S is countable. So among these four options, I can very well say for certain that S is countable in the first and fourth options. So those forms the answer for this problem. Those who have doubts can mark it down and ask at the end of the talk, so that you can. I will do as much as possible and give some time at the end of the talk. Now listen, a sequence is said to be bounded if some of the pictures that I have now I'm going to show you here are taken from the previous class slides, because those slides are very important, I felt, so I can't neglect them. So those who have attended complete last class can forgive me for repeating the slides here, but they are worthy seeing it again, so no problem. Okay, so if you take a bounded sequence, a sequence has to be bounded if all the terms, right from the first term as well as all the terms, like mod Sn is less than or equal to capital M for all n. You can't leave some terms away from this. In other words, a sequence is said to be bounded if every term of the sequence, right from the first term and all the terms, is packed between two finite strip. That is, all the terms is between, say, -1 to +1, or it's between 0 to 1, or it's between -2 to +2. If it can be, if all the terms are put between two numbers like small k and plus k here, where these two are finite numbers, you are packing all the terms of the sequence between two finite values, and therefore the range of the sequence mod Sn will be less than or equal to difference between capital K and small k. So it is not more than this. Therefore, such a sequence is a bounded sequence. Whereas this sequence is not bounded, because you see these terms here are between 0 and k, but the term which comes here goes endlessly. It drops down. It decreases as much as possible. Okay, so this is not a bounded sequence, the right hand side, whereas this is bounded sequence, because no terms here can escape between these two values. Whereas here, these terms here are between 0 and k, but these terms are going away from this range. So this is not a bounded sequence. Now in this question, which is a part B in one of the previous year papers, we are asked to, this is a wonderful question. I mean, when I solved this, it took some time for compared to other question that I have been solving yesterday. This question took quite a bit of time for me. I could not guess the answer immediately. It consumes a little bit more than what I usually do. Okay, it's a very tricky question. Suppose that xn is a sequence of real numbers satisfying the following. For every epsilon greater than 0, there exists n naught such that difference between xn plus 1 and xn, the xn and the next term is xn plus 1. So difference between successive terms is less than epsilon for all n greater equal to n naught. Then what can you say about the sequence xn? Is it bounded but not Cauchy, or it is Cauchy but not bounded, or it is convergent, or it is necessarily not necessarily bounded? It may or may not be bounded. The fourth option says it may or may not be bounded. In some cases xn may be bounded, some cases it may not be, not compulsory. So which among, say if you know that a sequence is convergent, in any convergent sequence is bounded, so automatically you get all those things. And with respect to sequence of real numbers, any convergent sequence is a Cauchy sequence, and any Cauchy sequence is a convergent sequence. So with this idea, I can just say, because the first option is bounded but not Cauchy, second option is Cauchy but not bounded, the answer third option cannot be correct answer, because if it is convergent, if my sequence is convergent, then it is bounded as well as Cauchy, because any Cauchy convergent sequence of real numbers is Cauchy, but both conditions were not given in any of the options here. Okay, so I know now, because the part B question, only one answer is correct, but I know that third option is not correct. Okay, you can think about it. So you define a sequence like this: xn is log 1 by n. Then if you take difference between successive terms n, xn plus 1 and xn, you get this, and this number is very close to 1. You see, as n is large, this is very close to 1. So you get this condition less than epsilon only if n is very large, n greater than equal to n naught, which means n is so large only after some stage, which I told in the previous class, if you remember. So this ratio is almost 1 if n is very large, and log 1 is almost 0. So this is less than epsilon whenever n is very large. So this condition is satisfied here, but unfortunately this is unbounded, because when you take n smaller number, this sequence is actually log 1 by n is minus log n, and this is not bounded sequence, because if n is large, log n becomes very large, and if n is small, 1 by n becomes very small, and log 0 approaches to minus infinity. So whenever you approach, whenever you take smaller numbers and approach to 0, this goes to thing, or you can write this as minus log n, and if you take n as very large number, log n is a divergence sequence, and therefore this is not bounded. Log n of course goes to infinity very, very slowly compared to the other terms. Okay, so it's not bounded, but it satisfies all these conditions. Okay? In fact, this is a Cauchy sequence. So not necessarily bounded is obtained in two options. Okay, but it is not Cauchy. You can see if you take x m plus n minus xn, and if you take m to be away from n, then you don't get this to be less than epsilon. You can check it later on. See, the difference between two successive terms, of course, is less than epsilon. But if you take difference between say 100th term and 50th term, or say 1000th term and 100th term, it may not be less than epsilon always, because log n is very, very slowly increasing. It doesn't jump quickly like n or n square or something. Okay, so it's a very clever question. One of very good question that is asked in the previous year paper. So the answer for this problem is the fourth option, not necessarily bounded. Now, if you take limit suprema, again, this is a repetition of what the picture that I showed in the previous class. But for those who missed and for those who can't understand properly, can do this. The supremum from the smaller collection or return like roof value here, and limit of supremum is the GLB value of this top values. So if you consider this as ceiling of some room, you take the least ceiling, that is limit supremum. Supremum is ceiling at different parts, and limit supremum is the lowest possible ceiling. Okay. Similarly, infimum is the ground part or floor part, and limit infimum is the largest of the floor part, largest floor. So supremum of this infimum value, that is limit infimum. Okay. So let us take another. This is another very good problem that I found in the previous paper. This is in part C actually. It's a very nice question. I think this was asked in December 2018 paper. Let Pn denote the nth prime number when we enumerate the prime numbers in the increasing order. That is, P1 is 2, P2 is 3, P3 is 5, P4 is 7, P5 is 11, as you know. So this prime numbers are increasing sequence of numbers. You define capital S to be set of all Sn which is difference of n plus first prime to n prime. So you subtract n prime from the n plus first prime. That difference is Sn. S contains terms which are difference of successive prime numbers whenever n is greater or equal to 1. Then what can you say about S? And what can you say about this Sn or something like that? Okay. First, if you try to construct the set S, actually, see what you get. The first element 1 is the difference between second prime and first prime. The S1 is P2 minus P1. The difference between second prime and first prime is 3 minus 2, that is 1. The second element is difference between third prime and the second prime. That is 5 minus 3, that is 2. The third element is difference between fourth prime and the third prime. S3 is P4 minus P3. So this is 3 minus 2. This is 5 minus 3. This is 7 minus 5. This is 11 minus 7. The next prime, fourth prime is 11. And the preceding prime is 7. So 11 minus 7 is 4. And this is 13 minus 11. The prime number which comes after 11 is 13. So 13 minus 11 is 2. And this is 17 minus 13. And this is 19 minus 17. This is 23 minus 19. This is 29 minus 23. And this is 31 minus 29, and so on and so forth. So this will be, in fact, these are all more collections of S. If you extend the collection of S, you get this numbers. What we call sequence of prime gaps. This is called sequence of prime gaps because difference between primes. Okay, this is how the prime numbers differ as you go along the set of prime numbers. Okay, now you can see clearly when you move on, the least number is clearly 1 because 2 and 3 are the only consecutive primes. There are no consecutive primes beyond 2 and 3 in any prime number list. If you take any two prime numbers, their minimum difference will be 2 except the first two primes. So the least difference that can occur between prime numbers, especially successive prime numbers, is just 1, and that happens only if you take 2 and 3. Whereas if you take some other prime like 3 5 or 5 7 or 5 11, whatever it is, if you take any prime for that matter, whether it's consecutive or non-consecutive, the minimum difference will be 2. And the minimum, apart from 2 and 3, the minimum difference is 2 because of the existence of twin primes. The prime numbers which differ by 2 are called twin primes. And I can tell you there's an interesting thing that though Euclid has proved that there are infinitely many primes in his Elements book some 2300 years ago, till today there is no exact proof for saying, though mathematicians strongly believe that there is such thing, there is no exact proof for showing that there are infinitely many twin primes. Though it's easy to show that there are infinitely many primes, the twin primes are prime numbers which differ by 2. Like for example 3 5 or 5 7 or 11 13 or 17 19 or 29 31. So this kind of collection where so twin primes can be written in the form p comma p plus 2. If p is a prime number, then twin prime pair will be written as p comma p plus 2. So they differ by 2 because there is always a prime twin prime factor pair that you can find along the number line. 2 comes infinitely many often. Not only here, this is 5 minus 3, this is 7 minus 5, but you see 2 comes infinitely many often, which means, and also the gaps between primes increases. Like for twin primes, the gap is 2, and the primes can differ by 4, the primes can differ by 6, the primes can differ by 8, the primes can differ by 10. Okay, so on and so forth. There are many primes. Say for example, primes differing by 10 you can easily give, for example 61 and 71, not consecutive primes of course, but you can always find difference between consecutive primes increasing by 2, like 2 4 6 8 10 12 and so on and so forth. Okay, there's no even number here apart from 1. After 1 you can't get any even number. The reason is simple, of course. I leave it as an exercise to students to think. 1 is the only odd number here. Apart from 1, all the other prime gaps are only even numbers. Minimum among them is 2, and this collection increases as, that is, you can find 2 successive primes whose difference is 100. You can find 2 successive primes whose difference is 1000. Any even number for that's always possible. Okay, because of the fact that you can always have any continuous of composite numbers between in any given range. Like you can always produce consecutive composite numbers, 1000 consecutive composite numbers. You can always produce 1 million consecutive composite numbers. Because of this fact, the difference between consecutive primes may be as large as possible. So keeping these things in mind, you see supremum of S is infinity, because we take supremum for the first element, that's infinity, for second element. So this numbers go without any bound. It's not bounded sequence. Therefore supremum of S is infinity. Whereas if you, so this being supremum is infinity, the limit, this is limit supremum is infimum of this value. Infimum of infinity is also infinity. So the first two options are obviously correct. Whereas if we take infimum of S, that is 1. You see, infimum of this collection is 1. So the third option is also correct. And if you take infimum of Sn, for the first element it is 1, from the second element and so on, it is either 2 or greater than 2. So if the infimum exists, it should be either be 2 or greater than 2. Okay. So because after the first element, infimum of Sn, you see it's either 2 or more than 2. Just now I told you 1 is the only odd number here, the other numbers are even numbers, and 2 is the least even number. So infimum of Sn is greater than or equal to 2. Okay. So this picture is again repetition of what I gave in the previous class. So if you want to find limit of a function whenever x approaches to a number, say c, so whenever x is between c minus delta to c plus delta, f of x should lie between L minus epsilon to L plus epsilon. The whole part of f of x should be between these two strips, that is L minus epsilon to L plus epsilon. Whenever x lies in the strip c minus delta to c plus delta. So if you take any x in this strip here, f of x should always lie between this particular strip. This is epsilon strip, this is delta strip. Okay, this is delta strip and this is epsilon strip. So whenever x lies in delta strip, f of x should be a number very close to L, which you call as a limit. In that case, I say limit of f of x is L as x approaches to c. And again, this are repetition because I need this to answer some of the questions that I'm going to discuss today. So 1 by x has no limit as x tends to 0, because when x tends to 0 plus, it approaches to plus infinity, and when x tends to 0 minus, it approaches to minus infinity. So limit of 1 by x as x approaches to 0 does not exist. Okay. See, limit does not exist can be viewed in several possible ways. Here, whenever x tends to 0 plus, that is to the right side of 0, the answer is plus infinity. The same thing happens to the left side also. And sine 1 by x or sine pi by x or sine 1 by x, whatever it is, does not have a limit at 0, because there are too many wiggles and oscillations here. So you can't fix a value. You know the theorem that if a limit exists, it should be unique number. So that uniqueness is not preserved here because of the too many wiggles that you find near 0. So limit does not exist. And here the limit does not exist is because the right hand limit at 0 turns out to be 1, and left hand limit turns out to be minus 1. Both exist, but they are not equal. So limit does not exist can be viewed in several possible ways. These are all examples of functions for which limit does not exist, but for different reasons. Okay. See, as I told you, the basic requirement for function to be continuous or to be differentiable is the existence of limit at the given point. If you know that, for example, a function does not even have a limit at a given point, or whenever x approaching to a certain point, there's no question of talking about continuity or differentiability. If limit even does not exist, you can't think about continuity or differentiability unless you make some changes in some possible cases. Okay. Now here the limit exists. The limit exists as x approaches to 0 for sin x by x. You see, left hand limit is 1, right hand limit is 1. But the function as it is not defined at x is equal to 0. When x is 0, you get sin 0 by 0, which is 0 by 0. There's one of the indeterminate forms, so that does not exist. So this is the definition of a function being continuous. See, this has a very big meaning here. Limit of f of x whenever x approaches to a means you see behavior of f near to x is equal to. So this equation conveys the fact that if the behavior of the function f near to a is equal to the behavior of f at the point, this is near to a, this is at the point. If f behaves as good as at the point to the near points, then f is said to be continuous. Behavior of f very close to a, this behavior of f at the point. If f behaves as good as at the points near to a as the point a, therefore then f is said to be continuous. So if the limit exists and if it's equal to the function's value at that point, then the function will be continuous. Now when you just take this function sin x by x and approach x tends to 0, the limit will exist, but as I told you, f is not defined at 0. Therefore, as it is, limit exists but not continuous. But you can remove this continuity, remove this discontinuity, and make it continuous by redefining it in the following way. You define f of x as sin x by x whenever x is non-zero, and define it 1 when x is 0. This 1 I have chosen because I know that the limit value is 1. When you redefine, you have to put a number here, which is the limit value. Okay, that we have got here through left hand limit and right hand. This 1 is the limit of the function through left side and right side. So I have to put this particular number here. So in this case, f of 0 becomes 1. The limit is also 1. So left hand side will become 1, right hand side will become 1, and therefore the function will become continuous. So you can remove discontinuity and make it continuous, provided if the limit exists. And unfortunately, the function is not defined at that point. If the function is not defined, you close this gap by assigning the same value at that point. Just patch it up. Just like if you have a small hole in your building or some room, you just patch it with some gum material or something, or some material should be added and close it. So this is the patching process here. So by doing this patching process, you can make discontinuous function to continuous, provided if the limit exists. And the function, so this type of discontinuity is called removable discontinuity, because you can remove the discontinuity and make it continuous. Okay. So this are examples as well as counter examples for functions which have certain nice properties. See, we have studied in your class that composition of continuous functions are continuous. So if you are given problems in net exam related to composition of continuous function, you should be careful in one way or two. I just give some not detailed example, but a short example. See, sin log x, is it a continuous function? To decide whether sin log x is continuous or not, I should probably guessed that log x is continuous, sin x is continuous, and you know that sine function is continuous for all real numbers. It doesn't have any problem with continuity. Sin x is a continuous function for every real number. Because the outer function is sine and log x is also continuous, composition of sine and log, which are two continuous functions, is continuous. And moreover, I know that sine is continuous for every real number. It doesn't lose its continuity for any x, any real number. Therefore, this graph here, which I have shown here in the red color or pink color, is always a continuous function. This pink color graph is continuous function. So this is a continuous function. So to guess whether some function, complicated function mixing with 2 or 3 values is continuous, you can view them as composition of functions and apply those ideas. Because log x is continuous and sin x is continuous for all x, it follows that composition of continuous functions are continuous. Therefore, sin log x is continuous. You see that I can't apply the same idea here for log cos x, though cos x is continuous and log x is also continuous. But unfortunately, you see the graph here in this is the graph of log cos x. It has several discontinuities. In fact, there are intervals in which it is not even defined. So this interval log cos x is not defined. This interval log cos x is not defined, and moreover, even in the defined intervals, it has infinitely many discontinuities. So there is a problem here. So the theorem says if the functions are continuous, then the composition is also continuous. But here I get discontinuity and function is not even defined for all. The problem comes because log functions are not defined when the domain is negative or 0. So if you can talk about log of something if that something is only positive number. So in other cases, you get this problem because log cos x is undefined whenever cos x is 0 or less than 0. You also know that cos x is some number between -1 to +1. Cos x has a range between -1 to +1. So log of cos x will not be defined whenever cos x is between -1 to 0. It is defined at the points whenever cos x is between in the open interval 0, 1. Okay, and these are the points where cos x becomes 1 because log whenever cos x becomes 1, you get log 1, 0. So those are the points that are marked here. Okay, the points where cos x becomes 1, this function becomes that is like x is 0, x is 2 pi, x is 4 pi. Such points where cos becomes 1, so log 1 is 0. But if you take points like cos x is negative, like cos pi is -1, so log -1 is not defined. So log of something is undefined whenever this value is a negative value. It is defined only for positive values. Even for 0, it is minus infinity, so it is not defined. So there comes the problem. So you can't always think that composition of continuous function is continuous blindly and apply that formula immediately. So you have to be very careful. The problem doesn't occur here because sin x has no restriction in the domain. It is continuous for all real numbers, whereas log x is continuous only when x is greater than 0. So in case of discussing problems like this, you have to be sure enough whether this term is non-negative or positive or 0, something like that. So the idea of continuity of basic functions are very essential. In other words, in what domain the function is continuous. That idea should be very or considered to be very important in discussing and analyzing about these concepts. Okay. About uniform continuity, I told in the previous class, again this is a repetition of previous class. Some of the students missed out, so for the sake of those things, I'm repeating here. So worth repeating. If you have a function like this, for a delta neighborhood, if the say whole part of the curve lies between epsilon neighborhood, if the whole portion of the curve lies for fixed epsilon and delta, the whole portion of the curve wherever you take always lies between this rectangular box, then the function is uniform continuous. So give me an epsilon, I will choose a delta such that if you draw a rectangle with that epsilon and delta as length and width, 2 epsilon and 2 delta, then if I get the condition that wherever you move along the curve, if the whole portion of the curve between those two delta values, if the whole portion of the curve lies in the rectangular box, wherever you take, then the function will be uniformly continuous. So you see here, for this function, for this case, the whole portion of the graph lies inside the box. For this portion, the whole portion of the graph lies inside the box. But for this portion, only up to this part, See, this is the whole portion of delta part. Up to this part, the graph lies inside, but when I move very close to the boundary here, it goes outside. So this portion of the graph goes outside the box. So this is not uniformly continuous, this function. In general, if you take a function which is rapidly increasing, such functions will be continuous but not uniformly continuous. Okay, but the increase should be very rapid, like e to the power of x or something. Now, for 1 by x, you see this is a very tricky value, 1 by x and root x. For root x, if you take any boundary here, whether you take values between 0, 1 or greater than 1, the whole part of root x always lies in this part, and therefore root x increases but very, very slowly, and therefore root x is uniformly continuous. Whereas 1 by x, if you take 1 by x very close to 0, the neighborhood of 0, this part of the graph will miss and this part of the graph will miss. I'll give few more examples. So 1 by x, whereas if you take 1 by x after certain number like 2 or something, whole portion of the 1 by x will come inside the box. So which means 1 by x is uniformly continuous whenever x is larger, but it's not uniformly continuous whenever x is small. So in particular, 1 by x is not uniformly continuous in the neighborhood of 0, in the interval, say in the open interval 0, 1, whereas it is uniformly continuous whenever x is greater than 1. Okay, that's how we have to do it. This is graph of sin x. For every fixed delta box, the whole portion of sin x lies inside the box wherever you take. Okay, so no portion of the curve goes beyond that box, and therefore this is uniformly continuous. Sin x is a uniformly continuous function. Similarly, cos x is also uniformly continuous. Now, if you take the graph of x square is uniformly continuous to the neighborhood of origin. In particular, if you take from 0 to 1, it is uniformly continuous. But if you take more than 1, there will be some missing portion. So for this delta box, you see the portion of the graph lies only up to this portion. This portion of the graph will miss. If you take values greater than 1, for such x square will become rapidly higher. So the portion of x square will be outside whenever x is greater than 1. It will go away from the box. So we conclude that x square is a uniformly continuous function in the interval 0, 1, but beyond 1, it is not uniformly continuous. Okay, so those are some of the very good things that you can observe through graphs. I showed this also. The 3 or 4 slides that I'm showing now are shown in the previous class also. Okay, so not new. So this is graph of e to the power of x. E power x is uniformly continuous whenever x is less than or equal to 0, but whenever x is greater than 0, you get some portion of the graph missing away, because e power x is a tremendously increasing function. Whenever x becomes large, e power x is very, very large. Exponential growth. So for exponential growth functions, the function will be continuous but not uniformly continuous, because say the portion of the graph will miss the same delta value because it's increasing very rapidly. Okay, now we'll solve a couple of problems before concluding this particular class. So you see, which of the following functions is uniformly continuous on the interval, open interval 0, 1? This is a part C question. We know that because you are given the interval 0, 1, the first choice I know from the graph that I have shown you, 1 by x is uniformly continuous whenever x is large, but whenever x is to the near to 0, the function increases rapidly. As you can see here, this is graph of 1 by x. This is why I took this picture again from the next class. From the previous class, I took this function graph because to answer this particular problem. So for answering this particular problem, I took this picture again and explained to some other graphs, because for the sake of students who missed previous class, the explanation part at least. See here, if you take values very close to 0, 1 by x increases rapidly. So any rapidly increasing function in the given interval will be continuous, but unfortunately may not be uniformly continuous. As you can see, the portion is missing out here. If the function is continuous and if it is rapidly increasing, it will not be usually uniformly continuous, though it is continuous. So you can see here, this portion of the graph is missing out. So 1 by x is not uniformly continuous in our case. What about x into sine 1 by x? This is a graph of x sine 1 by x. You know that x sine 1 by x is continuous. To answer this question, to answer uniform continuity, there are 2 tricks. One is to see by definition that same delta should work. The delta should depend only on epsilon, but not for the choice of x. So that is quite difficult for students' point of view, especially in discussing this kind of tricky functions. Okay, so I give two possible ideas to discuss uniform continuity. If you do not know beforehand the idea of how the function is going to behave, like 1 by x, 1 by x is easy to see. For x sine 1 by x, this is the graph. You can see near to 0. For I fixed a delta here. The whole portion of x sine 1 by x will lie in that interval. So there's no problem because function is not increasing. It remains constant. See, like this. So it remains almost like a straight line beyond certain value. It increases very slowly. So it's uniformly continuous. So second option is uniformly continuous. In fact, you can view this to the fact that x sine 1 by x is continuous in the closed interval 0, 1, and open interval 0, 1 is a subset of closed interval 0, 1. And you can conclude there's a theorem saying that if a function is continuous in a closed interval, then it is uniformly continuous in that closed interval. So if I know that f is continuous in a closed interval, say a comma b, then any continuous function on a closed interval will become uniformly continuous. Closed and bounded, of course, not just closed. It should be compact interval. If you take a function which is continuous, I'm sorry for just saying closed interval, it should also be bounded. So if you take any continuous function on a compact interval which is closed and bounded, then such function will be automatically uniformly continuous. Because we are discussing about 0, 1, that is a bounded interval, so there's no need to say bounded here in this particular case. So if I know that this function is continuous in the closed interval 0, 1, then that will be uniformly continuous. And in fact, this function x sine 1 by x is continuous not only at 0, but also at the point, at any points between, because I know, how do I know that? Because sine is a continuous function. Okay, x is continuous function. Product of two continuous functions are always continuous. There is some trick to guess whether the function is continuous or not immediately. Sine function is a continuous function. X is a continuous function, being a polynomial of first degree. Polynomial functions are continuous, so this product is again continuous. Okay, so this is continuous function in the closed interval. If you take any continuous function on a closed and bounded interval, that is compact interval, then such functions are automatically uniformly continuous, and therefore x sine 1 by x is uniformly continuous in the closed interval 0, 1, making it to be uniformly continuous in the open interval 0, 1 as well, because open interval 0, 1 subset of the closed interval 0, 1. And now for the third option, we know that sine 1 by x has so many wiggles, the limit even does not exist. You see, we saw in the graph here, this is sine pi by x, but sine 1 by x will behave in the same way, only the height will differ here. Okay, this height of the graph will differ, but the behavior is same. It has so many wiggles near 0. Therefore, sine 1 by x does not have a limit as x approaches to 0. We are talking about open interval 0, 1. Okay, so this function is not going to be our answer, because you see, we take delta strip here for sine 1 by x very close to 0. The oscillation is so high, the whole portion of the graph will not lie in the same delta strip, and moreover, limit does not exist whenever x is very close to 0. Infinitely many oscillations. So it is not, even if the limit does not exist, it is not continuous, and if it is not continuous, it is not uniformly continuous. So therefore, there is no need to talk about this function for uniformly continuous whenever x is very close to 0. And for sin x by x, this function has a limit as x approaches to 0. In fact, by redefining, as we did here, by removable discontinuity part, by redefining the function, I can make it continuous at 0. So you see, the sin x by x, this function is continuous in the whole interval 0, 1. Okay, by redefining this way, by removing the discontinuity and making it 1, you can see the sin x by x is continuous. Even if I do not know the graph, it's easy to see the sin x by x is continuous, because sin x is continuous function, x is continuous function, and division of two continuous functions are always continuous. Okay, so there's no problem. And I have removed the discontinuity at x is equal to 0 to make it continuous. So this function as it is continuous in the closed interval 0, 1. And as I told you, any continuous function on a compact interval of the form a comma b is always uniformly continuous. Here the interval is 0, 1. So it is uniformly continuous in the closed interval 0, 1. Therefore, it is also uniformly continuous in the open interval 0, 1. So the answers are second option and fourth option. Here the limit even does not exist, so forget about it. Here it is the function increases rapidly, so some portion of 1 by x will go out through this graph, so that is not uniformly continuous, though it is continuous. Okay, so among these four options, the correct options, the functions which will be uniformly continuous in the open interval 0 1 are second option and fourth option. In fact, this is the graph of sin x by x, the last part, and you can see very nicely for same delta value, the epsilon, the whole portion of the graph will lie between epsilon strip. No portion goes out. For this particular epsilon value, delta value, the whole portion lies inside this box. For this delta, no portion goes outside. So the function is uniformly continuous. And for the problem like 1 by square root of x, whenever x is positive, what happened? See, again here for 1 by square root of x, I have given the graph. I will answer this in two ways. If you know the graph of 1 by root x, 1 by root x behaves in a similar fashion to 1 by x. So whenever x is very small, 1 by root x becomes quite large. It increases rapidly. So whenever if you take any value of x in the neighborhood of 0, it will lose its uniform continuity. It will not be uniformly continuous. But the question is asking you not in a particular interval, general interval. So f is uniformly continuous on open interval 0 comma infinity will be false. Being a part B question, only one option is correct. Okay, so f is not uniformly continuous on open interval 0 infinity, because near to 0 the function will be continuous just like 1 by x, but it is not uniformly continuous. So first option is incorrect. So you can have another idea. So one of the idea to guess uniform continuity is to look at the graph and see. But if you do not in the exam, you don't have the portion of looking at the graphs, because you can't plot it like this, delta neighborhood and epsilon neighborhood. The boxes that we have conducted here, done here without any help of any software. So what you can do is you can apply two possible methods. One is you see whether a function is continuous in the closed interval containing this open interval. So for example, the given interval is 1 comma 2, you take the smallest closed interval containing it, namely closed interval 1 comma 2. So you take the smallest closed interval containing the given open interval, and then see whether if f is continuous in that closed interval. If you know that f is continuous on that closed and bounded interval, then by the theorem saying that any continuous function a compact set is uniformly continuous, therefore you can conclude that the function is continuous, uniformly continuous, as we did for this case, second and fourth option. Whereas the other idea to guess whether the function is uniformly continuous or not is again to see that you find the derivative of f, first derivative of f, like derivative of 1 by root x is 1 by 2 to the power x, 1 by 2 x root x, which is x power 3 by 2, and half is less than 1, so I rewrite this as this way. So if I take an x in the interval r comma infinity, then x is greater than or equal to r. In particular, if x is more than r, 1 by x power 3 by 2 will be less than 1 by r power 3 by 2. So the derivative is less than some finite number. Okay. If the derivative, first derivative is bounded in a particular interval, then f is uniformly continuous. So this is another way of looking at uniform continuity. One way to view uniform continuity is showing that it is continuous on a compact set. Okay. The other way to view uniform continuity is proving that the first derivative of f, namely f dash of x, is bounded in the given interval. So this is bounded in the given interval because it's less than something for all x. So for answer is the second option, because mod f of x is less than, as you can see here in this graph, once you go beyond certain stage. So if I take, say for example, r is 1, after 1 if you see the function is decreasing rapidly, or after 2 it is decreasing rapidly. So for all such cases there will be no missing parts like this. Once you take x values more than some number, like this number here or this number here or this number here, no portion of 1 by root x will miss the box that we construct. Whereas if we take boxes very close to 0, some portion will get missed out, meaning that in such cases, for such values of x, so this function is not uniformly continuous whenever x is very close to 0. But if you take x beyond certain number, it will be uniformly continuous because it decreases rapidly. So no portion of the function will miss out this from the box, and therefore it is uniformly continuous. The answer is the second option. So these ideas that I'm going to give here, that I have presented here, will be very useful for you to tackle many problems. Um, Being a member of the faculty in the department, I can tell you that this kind of classes are extremely important and useful to you, especially in nowadays we don't have had such provision of giving any classes. That too, you're getting it at free of cost. So my humble request to all the students participants is to make use of this classes, not only my class but other teachers classes, because those teachers have done this kind of work very effective in the past years, and it takes a lot of effort to solve these problems and present before you. So please make use of this to the most effective manner, so that you can pass in the future exam. So if you know the facts very clearly and know how to apply the ideas, see, any student know the idea, you could have done this as a theorem in your class, but in net exam what is important is to know how to make use of those ideas that you have done in the class. So if you know how to appropriately use them in the right problem and right place, you get the answer in no time. So that is where you need some practice and experience, and those experience were done here through these classes. So I request you to make use of this and not miss as much as possible in attending C4 classes. In upcoming classes also, we will be discussing new ideas and new topics. So I'm sure enough we'll be doing more justice than what is expected. It is only for the benefit of students. So please make use of this. And I conclude my class by thanking everyone for giving me this opportunity. Thank you.
Thank you, sir. We are lucky to have a resource person like you, sir. Your presence and experience gave more meaning to it. Thank you, sir. I would like to thank Professor R. Venkatramanan, Head PG and Research Department of Mathematics, for organizing the C4 workshop. I am very proud to inform about our next webinar titled An Introduction to Linear Programming Problems, Graphical Method and Simplex Method. Resource person Dr. Pragya Mishra, Assistant Professor, Department of Mathematics. PT Dean Dayal Upadaya, Government Girls PG Colleges, Rajajipuram, Lucknow, India. Will be held on 13th February at 10:30 a.m. Our next C4 session will be held on 13th February at 6 p.m. Thank you so much.